Hello guys, in this video we're going to be making a D-class stereo audio amplifier, and we're going to be eventually going to be making a Bluetooth speaker from this, and it's going to be a three-part series. In this first part I'll be detailing the general schematic and some of the design features. In the next video I'll be making a breadboard circuit and showing you how to do some of the more specifics, for example choosing values for the components. And in the third video I'll be showing you how to make a power system, install it in a case, and install Bluetooth functionality as well. At its basic level, a D-class audio amplifier works by turning an audio signal into a pulse width modulated signal and then turning off MOSFETs on and off to drive the power stage. But more specifically, this works with an audio input, an analog input, and then you generate a triangle wave and this goes into a comparator, and what this will do, this triangle wave is 200 kilohertz by the way, roughly. And what this will do is pull the output high whenever this is above the value of this triangle wave, and pull the output low whenever it's below the output of the triangle wave. So this will pulse width modulate your signal, and then this goes into a MOSFET driver, MOSFET or IGBT driver, and from here this will be powering an NPN MOSFET and a PNP MOSFET. I only draw them as boxes because I forget the symbol for a MOSFET. And then that will turn, this will be VCC here, which in my case will be 12 volts from a lithium polymer battery, a 3-cell lithium polymer battery. And this will go to ground here. This right here is the power stage, and your actual output will come in between these two MOSFETs, and this will be fed through a low pass filter. And what this will do is turn the pulse width modulation generated by here into an analog signal that a speaker will be able to interpret. And another additional note is, because speakers tend to not like constant DC signals, constant DC offsets, is you're going to want a coupling capacitor here, so a high pass filter essentially, on the output as well, just to remove the DC component of the signal. And this will go to a speaker. Specifically for this D-class audio amplifier, we're going to be getting our audio in, and then we're going to need to pre-amplify the signal. So we're going to use an op-amp preamp for this, and a non-inverting topology. And the op-amp we're going to be using is an LM471, Texas Instruments. There's a non-inverting type, potential divider gain, and the reason we're doing this preamp is because in order to control bass, treble, balance and volume, we're going to be using an LM1036 on this, and this requires an input, a minimum input of 1.3 volts, and an average voltage you'll get out of an audio jack from a phone, for example, would be 0.22 volts RMS. So yeah, we need to amplify this to 1.3 volts, so it can so we can use this chip here to control our bass and treble. And then in order to generate our triangle signal, we're going to be using a 555 timer. Let's call this VCC. 555 timer we're going to be using is an NE555, standard one. And out of here we get triangle wave. And the comparator we're going to be using is an LM2903. And the MOSFET driver we're going to be using is a TC4427, which can handle 2 inputs and 2 outputs. So we're going to be using 1 input and output pair for left and 1 input and output pair for right, so we can have 2 separate speakers, and this can drive the 2 stages separately. So if we have a look at the data sheet of the LM1036, we find this handy transfer function for the bass response, and there's also a transfer function for the treble response, G of J omega here. And this term AB here is determined by an external potentiometer, and it gives a maximum boost to bass when its value is 0, and a maximum cut to the bass when its value is 1. And the reason why we're doing this analysis is so we can determine the value of this capacitor CB. And if we have a look at the schematic in the datasheet, we'll see CB is this capacitor here. So we know that the transfer function can be programmed by adding an external capacitor here, and that's the value we're trying to find. So if we say we want a maximum gain / cut of 20 decibels when the frequency is 10 Hertz, say, for the bass, that's a very low frequency for sound. We need to find its gain and phase angle. We need to find the gain and phase angle of this transfer function, so we can do frequency response analysis on it. Now, if we manipulate the transfer function here into this form here, it makes it a lot easier to solve. And if we remember how to manipulate complex numbers, if it's in the form z equals a plus jb, the gain is the square root of a squared plus b squared, because this is what a complex number would look like. You can see there that using Pythagoras' theorem, it's just the square root of a squared plus b squared. And the phase angle here is the inverse tan of b over a. So in order to find what our gain is, we just do this formula to the top and bottom of the fraction and then just divide them. You can see here that it works out as the square root of 0.00065 squared plus omega cb squared over omega cb. And if we want to find the phase shift of a fraction like this, it ends up as using this formula on the top of the fraction, using the formula on the bottom of the fraction, and then subtracting the 2. So if we do that, we end up with the inverse tan of omega cb over 0.00065 minus the inverse tan of omega cb over 0. Now omega cb over 0 is infinity, and if we look at the limit as tan tends to infinity, tan to the inverse tan of x tends to infinity, we end up with 90 degrees, or half pi radians. And that does make absolute sense, because if the real component of the number is 0, then it's going to have a phase angle of 90 degrees here, and it's just going to be on the complex axis. So we end up with our phase equaling tan to the minus 1 of omega cb over 0.00065 minus 90 degrees, and that is for AB equals 0 or when bass is boosted to its maximum. Now we need to do the same thing for AB equals 1. That's when it's cut to its maximum, the bass is cut to its maximum, and we actually end up with the inverse of when it was boosted to its maximum, and that does make sense. We end up with 90 minus 10 to the minus 1 omega CB over 0.00065 and omega CB over the square root of 0.00065 squared plus omega CB squared. And that's for the gain there. If we look at the transfer function that the datasheet gives for the treble response, we get a similar scenario where we have AT here, which is determined by an external potentiometer, and CT here, which is determined by an external capacitor. And if we substitute AT equals 0 into this, we simply, this entire thing here works out as 1, and we simply get this formula here. So the gain is just the square root of 1 plus 5500 omega CT squared, and the phase shift is simply the inverse tan of omega times 5500 times CT. Now if we substitute AT equals 1 into this for the maximum treble cut, we simply get the inverse of what I previously just said. So we get the reciprocal of the other gain here, and we get the negative of the phase shift here. The first method I'm going to show you to determine these capacitances is the Excel method, because it's a software which most of you will be very familiar with using. And to do this, we're just going to choose two placeholder capacitances for the meantime so we can use them in our formulas. And then we're going to divide the problem into the gain and phase for the bass response and the treble response for maximum boost and maximum cut. And that will give us 8 different bode plots. Now we're going to want to enter the formulas which we derived earlier into Excel for varying values of frequency in hertz and radians per second. I've chosen to go up logarithmically 10, 30, 50, 70, 100, 300, 500, 700, etc., etc. The next step was to make the bode plots for this so we can tell how much gain for each frequency this system is going to have. I decided to make 4 plots, 2 gain, 2 phase, and I decided to put maximum boost and maximum cut on one graph so I can see the full range of the potentiometer as it changes. Obviously in this scenario you'd actually want to scale the axes logarithmically, and by the end of this what you can end up with doing is changing the values of capacitance which we used as placeholders earlier until you have your own tuned value for gain for each frequency. And I just used a trial and error method to achieve the results I wanted. The next method I'm going to show you is on Simulink. Here I have a simulation set up where on the left hand side of the screen the bottom scope is the input, the middle scope is the base adjustment, and the top scope is the final adjustment. The input here is a variable frequency sine wave. I have it set to about 640 Hz at the moment, and I have dials which vary some of the parameters, like the one I'm varying now is the base potentiometer. As you can see, the base gets cut when it's 1 at maximum cut, and it gets boosted when it goes back to 0. It gets boosted from 0.2 volts to 1 volt. And now because Simulink thinks it's an improper transfer function when AT equals 0, you can't adjust it completely to 0, but you can get close. So I actually had to restart the simulation here. There we go. But when it's very close to 0, you can actually see the treble has a lot of interference in it, and you have to account for that with the potentiometer. You can tune this response out. It's still kind of got quite a lot of interference on it, and you can tune this out by adjusting the values of your capacitances. Because this is a relatively low frequency, the value of this potentiometer isn't going to have too much of an effect on the actual gain. And as you can see, as I get lower and lower, you get more and more interference. In the simulation I also have dials for the capacitors, and as you can see, as I increase the treble capacitance, it actually cuts some of the interference out, and you increase a little bit of the gain. And this allows me to play with the capacitances until I find an appropriate value. I did notice that for appropriate frequencies, as you increase the value of the capacitance, the gain actually lowers, so you don't get a high gain for bass if you have a high capacitance for bass as well. And here I have it tuned relatively well for low frequencies. You can see there's still a little bit of interference as it comes out from the treble, and the bass gain at maximum gain is quite appropriate. To tune some of this, tune some of the interference out, I needed to increase the value of CT, or the treble capacitance. And you can see, because it's low frequency, it's getting boosted at the base, and the treble transfer function isn't having too much of an effect on it, apart from just creating interference. And also when it's set to maximum treble cuts, this also doesn't have too much of an effect on the wave, because again, it's quite a low frequency at the moment. So if we change this to a higher frequency, we have it set to maximum treble cut. Change it to a higher frequency, you can see that the treble is having a large effect on how on the output of the transfer function. And as you increase it, you increase the treble boost, and as you approach zero again, you get more interference. So I have these capacitances tuned relatively well at the moment, and I'm quite happy with them. So once you're done, if you've previously created a variable in MATLAB called CB and CT, they'll show up here, and you can just read them off the workspace and then choose the most appropriate value for capacitance.